Good morning everyone. In today's video we are going to discuss a topic from grade 12 chemistry. The chapter that we're going to do today is haloalkanes and haloarenes, and in this video I am going to cover the topics classification, nomenclature and preparation of haloalkanes and haloarenes. So first let us start with nomenclature of haloalkanes and haloarenes. So when we talk about the nomenclature, we have specific rules for each organic compound, and for haloalkene and haloarene, the name itself is the rule for the nomenclature. So for example, if I take haloalkene, haloalkene is the word that we use for the IUPAC nomenclature. So in the place of hal, we need to replace the name of the halogen. You know that all the halogens end with INE. For example, fluorine, chlorine, bromine, and iodine. There is astatine and tennessine as well, but these are not very common for grade 12. Now, in the place of hal, we need to replace these words. However, we need to remove the last three letters, that is INE. And if you remove these last three letters, you will get the words fluor, chlor, brom, and iode. So these words need to be replaced in the place of hal. So wherever you see hal in any of the nomenclature rules, not only for haloalkanes and haloarenes, for any other name also, if you find hal in the nomenclature rule, then you need to replace these words. Then we have alk. Alk refers to the number of carbon atoms which are present in the haloalkene. So you have studied the word roots for the number of carbon atoms in grade 10. So I will repeat it. For one carbon atom, we need to replace alk with meth. For 2, we replace it with eth. For 3, we use prop. For 4, we use bute. For 5, we use pent. For 6, we use hex. For 7, we use hept. For 8, we use oct. For 9, we use non. And for 10, we use dec. These are the commonly used word roots in grade 11 and 12 chemistry. However, I will tell you two more, that is undec and dodec. Undec and dodec are the word roots for 11 and 12 carbon atoms in the chain. So I think in grade 11 chemistry in hydrocarbons, there was an example of dodecane in pyrolysis. So that is why I have told these two words as well, as an example was discussed in grade 11 in the NCERT textbook. Now, let us go back to the nomenclature. So here we have seen what hal refers to and what alk refers to. Ane is basically the primary suffix for any alkane, and we also need to incorporate the letter O in between the hal and the alk. There is an O as well. So let's say I have a compound C3H7Br. So if you see here, there is an alkyl group attached to a halogen atom. So this is a haloalkene. Now, what is the halogen attached? It is bromine. So in the place of hal, I need to replace the word hal with brom. And then we need to add the letter O. So I will write bromo. After that, it is alk. And I told you in the place of alk, we need to replace the corresponding word root. So here, if you see, there are 3 carbon atoms present in the propyl substituent. So as a result, we need to replace the alk substituent with prop. So the word alk needs to be replaced with prop. And then we end the name with ane. Ane is the suffix for any alkane or any alkyl substituted chains. Now, this is the name and this is the IUPAC approved nomenclature. The trivial name, that is the common name, is alkyl halide. This is the rule that we follow when we are writing the common name. So again, I think it is clear that in the place of alk, we replace the word root, and in the place of hal, I told you we need to write the name of the halogen, but we need to remove the ine suffix from that. So the name of this compound according to common nomenclature will be propyl bromide. Propyl bromide is the name in IUPAC nomenclature. This is about haloalkanes. Now we can go to haloarenes. So again, for haloarenes, I told you it is the same thing. The name itself is the nomenclature rule. So for haloarene is the nomenclature rule. Again, I told you wherever you see the word hal, you need to replace it with the halogen name, but we need to remove the last three letters. So that is known to us. Now here the new term is arene. You have studied in grade 11 that arenes refer to aromatic hydrocarbons. And there are many kinds of aromatic hydrocarbons like furan, pyran, and also there is azulene. But the commonly known aromatic hydrocarbon is benzene and its derivatives. So whenever we say any compound which has an aromatic group, we normally consider it to be benzene because that is the simplest and the most common one. So let's say I am taking the example of benzene attached to a halogen. Let's say the halogen is chlorine. So here if you see, the arene is actually benzene and the halogen attached to benzene is chlorine. So in the place of hal, we will write chlor. And then there is an O in the nomenclature rule. So we will add that O. So the name is now chloro. And then we need to write the name of the aromatic hydrocarbon. So here the aromatic hydrocarbon is benzene. So we will write benzene along with the name. So hence the final name of this compound will be chlorobenzene. If you are talking about the common nomenclature, we need to follow the name aryl halide. So aryl is the name of the aromatic substituent. So here if you see, the substituent is a benzene ring. It is C6H5 and I think it is known as per grade 11 chemistry textbook. You have studied that benzene as a substituent is known as phenyl. So commonly many people make the error of considering this to be benzyl. Benzyl is not this. When we say benzene is a substituent, we always use the term phenyl. Benzyl on the other hand is toluene with one free valency. So if we are having a toluene chain, toluene is benzene with CH3. If we are substituting one of the hydrogens here with chlorine, then this is known as benzyl chloride. So benzyl refers to toluene with one free valency, whereas phenyl refers to benzene with one free valency. So here if you want to name chlorobenzene according to trivial nomenclature, the name will be phenyl chloride. So this is the nomenclature rule for haloalkanes and haloarenes. Now we need to discuss the classification. So first we need to discuss the classification based on the number of halogen atoms. Based on number of halogen atoms. So first we can discuss about monohaloalkanes or monohaloarenes. So monohaloalkanes or monohaloarenes are basically haloalkanes and haloarenes having one single halogen atom. So I think both the examples that we learnt earlier, that is bromopropene and chlorobenzene, are examples of monohaloalkanes and monohaloarenes. The second one is dihaloalkanes or dihaloarenes, and these are basically haloalkanes and haloarenes having two halogen atoms. So for example, if I consider C4H9 CH2Cl, and I am replacing one hydrogen here. Let's say it is CH3 CH2Cl CH2Cl. So this is an example of a dihaloalkane. If you see, there are two halogen atoms, one in the first carbon and one in the third carbon. So the name of this compound will be 1,3-dichloro, and there are 4 carbon atoms in the chain. So the name will be butane. So this is the IUPAC nomenclature. Similarly, an example of a dihaloarene will be 1,2-dichlorobenzene, where the two chlorine atoms are adjacent to each other, and the common name of this will be ortho-dichlorobenzene. Again, ortho, meta and paro is something which you would have learnt in grade 11. So I hope that is clear. Since the two carbon atoms are in the adjacent position, we will call this compound as ortho-dichlorobenzene. Now the third one is trihaloalkane or trihaloarene. So if there are 3 halogens, then it will be referred to as trihaloalkane or trihaloarene. So let's say if I take benzene 1,2,3 trichlorobenzene, this is an example of a trihaloarene. Similarly, if I take CH3 CH2Cl, CH, not CH2, CHCl, CHCl, CH2, CH2Cl. If I take this compound for the example of trihaloalkane, you can very well see that there are 3 halogen atoms. So it is a trihaloalkane, and the name of this compound will be 1,3,4-trichloro-pentane, because there are 5 carbon atoms in the main chain. So it is pentane, and there are 3 chlorine substituents. So I hope the classification based on the number of halogen atoms is clear. Then we have to discuss the classification based on the sp3 hybridized carbon halogen bond. So we have studied about hybridization in grade 11, and we need to first understand what is sp3 and sp2 hybridized CX bond. So let's say if there is a carbon atom attached to 4 single bonds, then here you can see that all the carbon bonds are sigma bonds. So, since there are 4 sigma bonds, the hybridization will be sp3. Let's say there is a carbon atom which is attached to 2 single bonds and 1 double bond. You have studied that when we are considering a double bond, one of them is sigma while the other is pi. So pi bonds are not considered in the hybridization. So here if you see, the carbon atom is under the hybridization of sp2 because there are only 3 sigma bonds. And if you consider a triple bond, then you know that in a triple bond, one of them is sigma while the remaining ones are pi. So if you have a carbon with a triple bond, then that carbon is under sp hybridization. So this we have studied in grade 11. So now let us talk about the classification based on sp3 hybridized CX bond. So based on the sp3 hybridized CX bond, first we have alkyl halides. If you consider C3H7Cl, here you can see that the carbon which is attached to the halogen has 4 sigma bonds. So there are 4 sigma bonds here, as you can see. So this carbon is under sp3 hybridization. So this is an example of a a haloalkane having sp3 hybridized CX bond. The second one is allyl halides or allylic halides. If there is a halogen which is attached to an allylic carbon, then it is an allylic halide. So let us first understand what is an allylic carbon. An allylic carbon is an sp3 hybridized carbon which is attached directly to a double bond. In other words, you can also say an sp3 hybridized carbon which is attached directly to an sp2 hybridized carbon is known as an allylic carbon. So I will give an example. I think that will be more easier to understand this term. So if I take the example of let's say Cl H C H CH2. Let's say I'm taking this as my example. So here if you see, there is a halogen attached to a carbon atom, and this carbon is having 4 sigma bonds around it. So it is under sp3 hybridization. But if you look at the carbon next to it, this carbon has only 1, 2 and 3 sigma bonds because it is having a double bond. So as a result, this carbon is under sp2 hybridization. So in this case, this carbon atom which I am circling is the allylic carbon. And this is an example of an allylic halide. This compound is an allylic halide. And the name of this would be 3-chloro-prop-ene or prop-1-ene. That would be the name. Now let us go to the next type of haloalkanes, that is benzylic halides. Again, even in benzylic halides, there is a halogen attached to an sp3 hybridized carbon. Now, when I say benzylic halide, it means it is attached to an sp3 hybridized carbon, which is which is directly attached to an aromatic ring. So, for example, if I consider benzyl chloride. As I told you, benzyl means it is toluene with one free valency. And when I say benzyl chloride, one of the hydrogens is replaced with a halogen. So let's say I am replacing it with chlorine here. So if you see, there is a benzene ring, and this benzene ring is directly attached to a carbon atom, and this carbon has a halogen attached to it. Again, if you see, this carbon is still under sp3 hybridization. However, it is directly attached to an aromatic benzene ring. So this carbon is known as a benzylic carbon, and this compound is an example of a benzylic halide. I hope this is clear, and the name of this compound will be benzyl chloride. So this is about the classification based on sp3 hybridized CX bond. The last classification will be on the basis of sp2 hybridized CX bond. So we have only two types. One is vinylic halide and the other one is aryl halides. So let me first discuss aryl halides, because that is basically something which we have already discussed. So any normal haloarene is known as an aryl halide. So for example, chlorobenzene. If you see here in chlorobenzene, the chlorine atom is attached to a carbon which has a double bond on one side. So since there is a double bond on one side, it only has 3 sigma bonds because the other bond is a pi bond. So as a result, this carbon is under sp2 hybridized CX bond or sp2 hybridization. Next, we have vinylic halides. Vinylic halides are haloalkanes which are attached to a halogen. However, they only have 3 sigma bonds because they are a part of a double bond. So, for example, if I say CH2 double bond CHCl. If you see the carbon which is attached to the halogen, it only has 3 sigma bonds, 1, 2 and 3, because here the double bond also has a pi bond in it. So as a result, this carbon is under sp2 hybridization and it is known as vinylic carbon. So this is an example of a vinylic halide and the name would be chloroethene. So here the carbon is a part of a double bond and it is attached to a halogen, so it is a vinylic halide. So these are the examples of the haloalkanes and haloarenes, and we have studied the classifications. Now we need to discuss the preparation of haloalkanes and haloarenes. So first we have to study the preparation based on the preparation of haloalkanes. We have to study preparation of haloalkanes. So first we have preparation from alcohols. So how can we prepare haloalkanes from alcohols? So first we can use Lucas reagent. Now Lucas reagent is nothing but concentrated hydrochloric acid with zinc chloride catalyst, concentrated HCl with ZnCl2. This is known as Lucas reagent, and this is one of the most effectively used reagents to convert alcohols to haloalkanes. So, if I want to convert an alcohol, let's say I am taking ethanol, for example, and I want to convert it to chloroethane, then I can just add concentrated HCl in the presence of zinc chloride. This is known as Lucas reagent, and this will effectively convert an alcohol into a haloalkane. You can even use HBr or HI, but commonly this is used for conversion into chloroalkanes only, because Lucas reagent always has zinc chloride in it, so we commonly use this for chloroalkanes. However, if you're adding HBr to ethanol, it will be converted into bromoethane. Also, this is something which is very important, because if we are using a tertiary alcohol, then the zinc chloride catalyst is not required, because tertiary alcohols will react with Lucas reagent easily and it will produce immediate turbidity. That means a precipitate will be formed immediately. So for tertiary alcohols, you do not require zinc chloride, but for secondary and primary, you need to add zinc chloride as well. Secondary alcohols will show turbidity slowly. It won't be very fast. It will take some time. Primary alcohols will not react with Lucas reagent at all if the temperature isn't elevated. So at room temperature, if you're performing this experiment and you're adding Lucas reagent to a primary alcohol, then you will not find any kind of precipitation taking place. So if you want to convert a primary alcohol into a haloalkane using this method, then you have to increase the temperature, and only at maybe 100 degrees Celsius or some kind of elevated temperature, this reaction will work. The second one from alcohols is by using phosphorus trichloride. Now, phosphorus trichloride is also one of the methods which we use to produce haloalkanes in great numbers. So if I have 3 alcohols and if I'm adding phosphorus trichloride, then you will be able to see that 3 molecules of haloalkane will be produced, and the byproduct will be H3PO3. H3PO3 is known as phosphorus acid. Phosphorus acid is the byproduct, and you can effectively produce a large number of haloalkanes from this method. You can even do this with phosphorus tribromide. Phosphorus tribromide can be used to prepare bromoalkenes. The third method is by using PCl5. Now, this method is not possible with other halogens. It only works for chlorine. So, if you have, let's say, an alcohol like propanol, CH3, CH2, CH2OH, and if I am adding phosphorus pentachloride, then what happens is one of the halogens will get substituted and you will be getting C3H7Cl, that is chloropropane. The hydrogen will react with the other chlorine atom and you will get HCl as a byproduct. Then the remaining oxygen atom will join with the PCl3 group and you will get POCl3 as the byproduct. POCl3 is phosphoryl chloride and that is also one of the byproducts. And again, this method works only for chlorine. The fourth method is by using SOCl2. SOCl2 is known as thionyl chloride. Thionyl chloride. So if I'm having an alcohol, let's say butanol, C4H9OH, and if I'm adding thionyl chloride, then what will happen is HCl will be produced. So one of the chlorine atoms will react with the hydrogen and HCl will be produced. The oxygen will join with the SO group and as a result you will get SO2, sulfur dioxide. Then in the thionyl chloride there is one chlorine remaining and this will join with the butyl substituent and you will be getting C4H9Cl, that is chloroputane. So this is another method of preparing haloalkenes. Again, this is only for chloroalkanes. The fifth method is to convert alcohols to bromoalkanes. So for this we can use sodium bromide in presence of concentrated sulfuric acid. So if you are having an alcohol, let's say ethanol, and if I am adding sodium bromide in presence of concentrated sulfuric acid, then you will be seeing that there is formation of NaHSO4. NaHSO4 is sodium bisulfate. So this is one of the products which will be produced. Then you can also see that bromoalkane will be produced. So in this case, since we're taking ethanol, you will be getting bromoethane as the product, and this is the main product that we want to get. And then the other byproduct that will be formed is H2O. So Ne will react with the sulfate group and it will form a sulfate and hydrogen and it will form NaHSO4. You have one hydrogen remaining which will join with the alcoholic OH group, and then you have only an ethyl group and you have a bromine halogen. So this bromine halogen will attack the ethyl carbocation and as a result you will be getting bromoethane. And bromoethane is the main product because we want to prepare haloalkanes. Then the last method to prepare haloalkanes is by using halogen in presence of red phosphorus. So this is the last method to prepare haloalkanes from alcohols. So here this method is used only for two halogens, that is bromine and iodine. So you cannot use this method to prepare chloroalkenes or fluoroalkenes. So let's say I have CH3, CH2, CH2OH, propanol, and I am adding I2 in presence of red phosphorus. Phosphorus exists in two forms. One is the red phosphorus and the other one is the white phosphorus. But here we specifically need to use red phosphorus. And what will happen is you will be getting CH3, CH2, CH2I, that is iodopropane, and this is our main product. There are several byproducts formed and these are highly reactive, and these byproducts are not very significant, because it depends on many factors like the temperature and the weather conditions. So there are many factors which determine the byproduct. So mainly in this reaction you need to mention the main product, that is the iodoalkane or bromoalkane. Now, other than these, there are many other methods like using concentrated HBr, 48% concentrated HBr to produce bromoalkanes. Also, you can use orthophosphoric acid also to prepare haloalkanes from alcohols. So there are many other methods, and also for iodoalkanes you can even use potassium iodide or sodium iodide as well, and that can also be used to convert alcohols to iodoalkanes. But these are the major six methods to prepare haloalkanes from alcohols, and these are the reactions which are given in the textbook as well. So after this we need to discuss the preparation from hydrocarbons. So first we can discuss under hydrocarbons, we need to discuss from alkanes. So you have studied in grade 10 that if you have an alkane, let's say methane, and if you are adding halogen gas in presence of UV light or sunlight, then you will be able to see that HCl is released and you will get CH3Cl, that is chloromethane. So this is known as free radical substitution, and free radical substitution is used to convert alkanes to haloalkanes. So here it is very simple. One of the hydrogens will be replaced by a halogen atom, and this is very important because if this substitution takes place in aromatic hydrocarbons, then we have to be very careful. So let's say I am taking aromatic hydrocarbons like let's say chloro or ethyl benzene. Now if I take ethyl benzene and if I am doing this same method, that is adding halogen in presence of heat or UV light, then you can see that HCl will be released and one of the carbon atoms will have the chlorine substituent. Now here you have to understand that always the carbon which is directly attached to the benzene ring will be substituted. So in this case the product will be benzene with CHCl CH3. This is the product formed in this case. So always the first carbon which is directly attached to the aromatic ring will undergo substitution. And the other important thing which you need to keep in mind is that if this same reaction takes place in presence of a Lewis acid, like let's say anhydrous aluminium chloride, if you are using a Lewis acid, then this is electrophilic substitution. It is no longer free radical substitution. It will undergo electrophilic substitution reaction, and as a result the chlorine atom will be attached to the benzene ring in the ortho and the para position. So you will get orthochloroethylbenzene, and also you can see parachloroethylbenzene. So you will get ortho and para substituted product if you are using a Lewis acid, because when the reaction takes place with Lewis acid, it is electrophilic substitution. So the compound will undergo chlorination or bromination, and as a result you will get a halogen substituted in the benzene ring itself. But if you want the halogen to be substituted in the alkyl group, then you have to use heat or sunlight or any UV light. The second method of preparation from hydrocarbons is from alkenes. Now again from alkenes you have some other methods. So the first one is by using hydrogen halide, that is HX. So if you are having an alkene, let's say propene, and if you add a hydrogen halide, let me take the example of HBr, then you know that this is an example of Markov-Nikov's addition. So we need to follow Markov-Nikov's rule, and according to Markov-Nikov's rule, if hydrogen halide is attached to and is added to an unsymmetrical alkene, then the negative part of the addendum will go to the carbon atom having lesser number of hydrogens. So here if you see, the reacting site is the double bond. So the halogen will attack their doubly bonded carbon atoms. But according to Markov-Nikov's rule, the halogen can attack only the carbon having lesser number of hydrogen atoms. So as a result, you will be getting CH3, CH, Br, CH3. So the positive part of the addendum will go to the carbon with more hydrogens, and the negative part of the addendum, which is bromide in this case, will go to the carbon with lesser number of hydrogens. So this is Markov-Nikov's rule, and this is something which you have already learnt in grade 11. So I hope you are aware of this rule. Then the next kind of reaction is by using HX in presence of peroxide. So you have many kinds of peroxides like hydrogen peroxide or benzoyl peroxide and so on. So whatever peroxide is used, always this reaction follows anti-Markov-Nikov's rule, and this is known as Karash effect or peroxide effect. You have already learnt this in grade 11. So I am going to explain it with an example. So let me take the same alkene propene itself, and I am going to write HBr in presence of a peroxide. It can be any peroxide, maybe H2O2 or acetyl peroxide or benzoyl peroxide, C6H5 twice O2. So whatever peroxide is used, you can follow anti-Markov-Nikov's rule to determine the products. So in this case, the negative part of the addendum is bromide, and according to anti-Markov-Nikov's rule, the negative part should go to the carbon atom with greater number of hydrogens. So you will see that the product is CH3, CH2, CH2Br, that is 1 bromopropane. Here the product is 2 bromopropane. Here the product is 1 bromopropane. That is the difference. So this is known as anti-Markov-Nikov's rule. And again, one more thing which is important is that this is applicable only to HBr. You cannot use HI or HCl when you talk about anti-Markov-Nikov's rule. But Markov-Nikov's rule is applicable for all the hydrogen halides. Then the third method is by using bromine water. Again, this is still under alkenes. We have not yet finished alkenes. We are still in alkenes. So if I use bromine water or bromine in presence of carbon tetrachloride, we need to see what is the product. So let's say I am taking ethene. If I take ethene and if I am adding bromine in presence of carbon tetrachloride, what happens is one of the bromines will go to the first carbon and the other bromine will go to the second carbon, and in the double bond the pi bond will be broken. So why the pi bond is broken is something which you have already learnt in grade 11. You know that pi bonds are weaker because they are formed by they are not overlapping extensively. They are following lateral overlap. So as a result, the pi bond is weaker. If you see the sigma bonds are stronger because they overlap using head-on overlapping or face-to-face overlapping. So the sigma bonds are more tight and they are more stronger. Hence, when you are cleaving the double bond, always the pi bond is broken first and only then the sigma bond will be broken. So here the pi bond will get cleaved and as a result the two halogen atoms which are there will attack either carbon atom. So one halogen will go to the first one and the other one will go to the second carbon. So as a result the product formed will be CH2, CH2, Br, Br. So this is a vicinal dihalide. Vicinal dihalide means in a compound if there are two halogen atoms which are attached to adjacent carbon atoms, then that is known as vicinal dihalide. So here if you see there are two halogens and the two halogens are attached to adjacent carbon atoms. So as a result this is a vicinal dihalide, and this can be used as a distinguishing test in order to distinguish between saturated and unsaturated hydrocarbons. So you have learned this distinguishing test even in grade 10, but even in grade 12 we use this test. So unsaturated hydrocarbons will undergo this reaction with bromine water or bromine in presence of carbon tetrachloride, and as a result you will be getting a vicinal dihalide. So due to that the original brown color of bromine will be decolorized because now there is a new compound being formed. But this reaction with bromine water is not possible with alkanes, that is saturated hydrocarbons. So as a result, saturated hydrocarbons will not show decolorization with bromine water because there is no such reaction taking place with alkanes. So as a result, the brown color of bromine will still be present. So these are the preparation methods from alcohols, and next we also discussed the preparation from hydrocarbons. Now the third method of preparing haloalkanes is it is through halogen exchange. So again there are two methods for halogen exchange, and both of these are very very important because these are named reactions. So named reactions are always very important because named reactions are frequently asked in the conversion questions, or any question related to organic chemistry will mostly be related to named reactions. Of course the other reactions will also be asked, However, the named reactions are more frequently evaluated in the board exam. So, the first method of halogen exchange is known as Finkelstein reaction. Now, Finkelstein reaction is used to prepare iodoalkanes. So, if you want to replace the halogen atom with an iodine atom, then we can use halogen exchange method, and that is through Finkelstein reaction. For Finkelstein reaction, we require a chloroalkane or a bromoalkane. So, for example, I am going to consider chloropropane. Now, if I want to convert chloropropane to iodopropane, then I need to add the reagent sodium iodide. Sodium iodide is the reagent, and sodium iodide will be used to convert chloroalkane or bromoalkane into iodoalkane. So, as a result, you will be getting the byproduct of NaCl or NaBr, and this is known as halogen exchange, and this particular reaction is Finkelstein reaction. Very important is one of the most important things here is that we need to mention dry acetone. Dry acetone medium is very important for this reaction because it will help in the precipitation of the NaCl or NaBr according to Le Chatelier's principle. So Le Chatelier's principle is something which you have learnt in grade 11 under equilibrium chapter. So according to Le Chatelier's principle, for the precipitation of NaCl and NaBr, we need to add dry acetone. So only in dry acetone medium this reaction will work. The second reaction under halogen exchange is Schwarz reaction. Now, Schwarz reaction is used to convert chloroalkanes or bromoalkanes into fluoroalkanes. So, this is the only method which we are learning to prepare fluoroalkanes. So far, I had not discussed any of the methods for fluorine because fluorine reactions are very reactive, and also they are quite explosive as well. So we normally don't use any reaction to prepare fluoroalkanes because the reaction is quite violent. But in this case, Schwarz reaction is one of the commonly used methods to prepare fluoroalkanes. So this is used to convert chloroalkanes or bromoalkanes to fluoroalkanes using metallic fluorides. So the metal can be silver, it can be antimony, it can be cobalt, or it can even be mercury. So from these metallic fluorides, you will be able to convert chloroalkane or bromoalkane to fluoroalkane. So let me take the example of ethyl chloride or chloroethane. So if I'm adding any metallic fluoride like AgF or Hg2F2 or COF2 or SbF3, then you will be able to see that C2H5F will be produced, that is fluoroethane, and the byproduct will be AgCl or Hg2Cl2 or CoCl2 or SbCl2. So depending on the metallic fluoride, your byproducts will be different, but the product will always be the alkyl group attached to a fluorine atom. And if you see, you might wonder why we are writing Hg2F2. According to crisscross rule, if we are saying Hg2 positive and F negative, Hg positive and F negative, then it should be HgF by cancelling it. However, here if you see, this is a dimer. Hg2F2 mercuric fluoride is a dimer. So as a result, since it's a dimer, the formula is not HgF, it is Hg2F2. So dimerization is something which we will be seeing under solutions lesson, and also even in aldehydes, ketones and carboxylic acids. Under the physical properties of carboxylic acids, we will be seeing that they form dimers. So dimers are basically two molecules which are linked together. So if you're having two molecules bonded together for extra stability, then that is called dimerization, and the compound is called a dimer. So in this case, Hg2F2 is a dimer. So that is all about preparation of haloalkanes. So far whatever we discussed was only for haloalkanes, not for haloarenes, and we discussed three major methods, that is from alcohols, from hydrocarbons and through halogen exchange. And under these three we learned many subdivisions, and all these are applicable only for haloalkenes. So always making a mind map or a flow chart for the preparation techniques, not only for this lesson, for all lessons, will surely benefit you, because it gives you a detailed summary of all the reactions, and you can remember what all techniques are applicable for which compounds and so on. So now we can discuss preparation of haloarenes. For preparation of haloarenes, we can prepare haloarenes from benzene and its derivatives. So if I'm using benzene or any other substituted compound, and if I am adding chlorine in presence of a Lewis acid like anhydrous AlCl3, then you will be able to see that a haloarene is formed and HCl will be removed. So this is the example. If I'm taking some other benzene compound, let's say propyl benzene. Now you are aware that alkyl group is an electron donating group, and electron donating groups are ortho para directing. So as a result, the chloronium electrophile, which is going to attack the benzene ring, will be shifted to the ortho position and the para position. So you will be getting HCl first. HCl is the byproduct, and as a result you will be able to find orthochloropropyl benzene and para chloropropyl benzene. And of course the para compound is more stable, because para isomers are symmetrical, they are having a symmetrical structure, and also they are having lesser steric hindrance because both the substituents are far apart from each other. But if you consider the ortho substituted compound, the two groups are adjacent to each other, so as a result there is more steric effect or steric hindrance experienced. So due to the lesser steric hindrance and because of the symmetrical structure of the para isomers, they can fit in the crystal lattice better, they can fit perfectly, and as a result para isomers or para substituted products are always major in quantity. Not only in this reaction, for any kind of substitution, if there is an ortho and para product formed, always the para is of greater stability. Then the last method of preparing haloalkanes is by using Sandmeyer's reaction. Now, Sandmeyer's reaction is basically something which we learn even under amines chapter, but in this lesson also we are learning this reaction. So the first step of Sandmeyer's reaction is diazotization. Diazotization is the process of converting aniline to a diazonium salt. So first of all, you know that aniline is benzene with an NH2 group. NH2 group is known as amino group. So this compound is known as aniline. Now, if I am adding sodium nitrite NaNO2 in presence of HCl, then you will be able to see NaCl being removed and two water molecules will be removed, and your final product will be benzene with N2Cl. Benzene with N2Cl will be the product. Now, benzene with N2Cl is known as a diazonium salt, and this particular compound is known as benzene diazonium chloride. Benzene diazonium chloride, and it is an example of a diazonium salt. So, azo actually refers to nitrogen. So if you see, there are two nitrogens here. So this is diazo. That is why there is a diazo term in the name. And why is it diazonium? So normally when we say em, it is for positive ions. So here actually, if you are expanding this bond, you can see that there is actually an ionic bond. There is an ionic bond between the nitrogen and the chlorine. So because of this ionic bond, this group is a diazonium group, and the diazonium group is attached to benzene, and also the anion is chloride. So as a result, the name is benzene diazonium chloride. Now this is the first step. Now the second step is actually Sandmeyer's reaction. That is, if you are having a diazonium salt like benzene diazonium chloride, and if I am treating it with Cu2Cl2 or Cu2Br2 or Ki or KCN, then this is Sandmeyer's reaction. So, when you are adding cuprous halides like Cu2Cl2 and Cu2Br2, what will happen is the byproduct is nitrogen, and also you may get Cu2Clbr or Cu2Cl2, and the substituted product will be benzene with chlorine or benzene with bromine. So you will be able to produce chlorobenzene and bromobenzene. For iodine, we do not use cuprous iodide. We use potassium iodide instead. And for cyanide also, cyanide is actually not a halide. However, I am just discussing this because you will be learning about KCN in amines under the same topic. So as a result, I am going to explain cyanide as well. So here Ki and KCN are used to prepare iodoalkenes and also cyanobenzene. So you will be getting benzene with iodide and benzene with cyanide group as the product if you are using Ki or KCN, and the byproduct produced will be KCl, potassium chloride. Now again here, if you see, I am writing Cu2Cl2 and Cu2Br2 because these are dimers. Actually, cuprous halide should be CuCl or CuBr, but in the dimer form, it will be Cu2x2. And another thing which I forgot to mention under the first method, that is from arenes. Here, if you see, there is one important thing, that is, if you are performing electrophilic substitution reaction with iodine compound, iodine and Lewis acid, then what will happen is you will be getting HI and an iodinated compound. However, you know that this reaction is reversible because iodine has a greater atomic size compared to the other halogens, and this reaction is reversible due to the big size of iodine. So since it is having a larger atomic size, the bond length in the HI and the iodinated compound will be very large. The bond length will be more. So because of this greater bond length, the bonds can immediately be cleaved, and the reaction is reversible, and it is slow as well. So because of this, what we have to do is that we need to use an oxidizing agent like HiO4 or maybe nitric acid. So these kind of oxidizing agents must be used in this reaction, and if you are adding an oxidizing agent, it will be oxidizing the HI which is formed, and as a result, what will happen is the reaction will only be shifted in the forward direction, and it will not be reversible anymore. So if you want to stop the reversible reaction, you have to use an oxidizing agent like HiO4 or HNO3, then the reversibility will be stopped because the HI formed is going to get oxidized. The HI which is formed will be oxidized. And also for the Lewis acid catalyst, it is not required that you have to use only anhydrous AlCl3. You can even use other Lewis acid catalysts like iron in presence of dark, like in absence of light, or you can even use ferric chloride or ferric bromide and so on. Any Lewis acid catalyst will work. So that is all about the preparation, classification and nomenclature of haloalkanes and haloarenes. So I hope this video was useful for you, and I hope I have covered all the topics. In case you are having any doubts regarding any of these reactions or any topic that we did today, please feel free to comment, and I will surely clarify your doubts. So thank you everyone, and stay tuned for the upcoming videos. Have a great day, and thank you.